training symposium. So next up, we will have Arlene Anderson from the Department of Energy tell us about this extensive foundational study called GeoVision that they have commissioned, and we'd like to know what they have learned so far. So take it away, Arlene.
Thank you, Lakshmi. How's the sound? Volume okay?
Good.
Great, great. Thanks, Lakshmi and Kristen, for organizing this very first educational webinar. And thanks, everyone online, for your time and attention. I really appreciate it. Lakshmi asked that I speak to you about DOE's GeoVision, harnessing the heat beneath our feet, as it relates specifically to low temperature geothermal. So I'll do that. And then I'll also touch on using low temperature geothermal resources for district heating, and then going a little beyond the GeoVision analysis. I'll mention feasibility studies that our office, the Geothermal Technologies Office, or GTO, funded that in the future could contribute to geothermal district heating and cooling. Amanda Kalker with the National Renewable Energy Lab, your next panelist, will provide more detail about our feasibility studies. I'll also discuss how the low temperature geothermal resources, when used for district heating and cooling, have the potential to address the needs of an evolving electric grid. And I'll end with a brief summary of the GeoVision roadmap, action areas needed to address those GeoVision objectives. And then I'll assign you some homework, if that's okay. Next slide. In 2019, GTO published the results of the GeoVision analysis. GeoVision, it was a very rigorous multi-year assessment of opportunities for geothermal in the US. Under a range of scenarios. And there is the address shown there where you can find it. You can also Google GeoVision harnessing the heat beneath our feet and it'll come up. We based our analysis on the detailed assessments of the geothermal industry, deployment barriers, and both existing and improved technologies. So, for example, an existing technology like district heating, let's take conventional direct use. There's 21 existing installations in the United States. So that's an example of an existing technology. And when we talk about improved technologies, we're really in the GeoVision looking at expanding the spectrum of where the geothermal resource might be available in this context. So the fundamental question that we wanted to answer is what level of deployment would be achievable and what would be the corresponding economic benefits to industry, and also what would be the environmental impacts of those deployment levels on the United States. So, and you can't really talk about economic impacts without talking about employment. So next slide. As of 2018, the US geothermal industry employed about 35,000 workers. The number has risen and it will continue, hopefully, with jobs often requiring technical skills and knowledge. And they tend to be well-paying. Pointing out the obvious, so the potential for geothermal deployment applies equally to the potential for geothermal employment. Next slide. According to the Bureau of Labor Statistics, occupational categories and some example positions in geothermal energy include sciences, engineering, drilling, construction, operations. So science, things like geologists and hydrologists, geochemists, ecologists, engineers, electrical, environmental, mechanical, drilling, rig operators, drillers, roustabouts, construction, carpenters, equipment operators, electricians, and operations, plant managers, suppliers, maintenance staff. So in addition to the science and technology jobs, there's a lot of entry-level jobs that could really lead to full careers for many people. Next slide. So the types of geothermal, I'll approach this differently than Mark to communicate more the spectrum of geothermal, starting with geothermal heat pumps, also called ground source heating and cooling or geo-exchange. Throughout the GeoVision, DOE refers to them as geothermal heat pumps. These are going to work on geothermal resources near ambient conditions or temperatures between 40 to 80 degrees Fahrenheit. And there's a spectrum of technological approaches as well, or development approaches, from excavating shallow trenches to drilling deep boreholes, and in some cases drilling wells. As Mark mentioned, the standing column well might be an example where there would be a well drilled for a geothermal heat pump, but in most cases it's going to be either a horizontal or vertical borehole, or maybe a shallow trench. And then the direct use option is mostly operating on a moderate temperature geothermal resource from about 100 to 300 degrees Fahrenheit. And these may require deeper wells, at least in the conventional sense right now with the technology and resource locations. They might require deeper wells aimed at district scale applications. So again, conventional direct use is mostly in the Western US, where the moderate temperatures are closer to the surface. And these are the existing direct use district heating systems that we looked at in the GeoVision. We didn't look at a range of new generation direct use district heating and cooling coupled applications, mostly district heating only. Then in the electric power area, this is mostly high temperature, greater than 300 degrees Fahrenheit. But more now, we are seeing the potential even for lower temperature power production. The geoheat flow, if you look at the graphic, you can see the spectrum of resources. The geothermal heat flow, it can be visible at the surface as a volcano, maybe as a fumarole or a hot spring or a geyser. But it can range from thousands of degrees to a few degrees above the ground surface temperature, making it a resource continuum. Much of the energy can be used productively, from geothermal heat pumps for heating and cooling, direct use for agriculture, and a wide range of district energy applications, all the way up to electricity generation. And as a renewable geothermal resource, diversity is the key to industry's continuous growth. Next slide. The results of the GeoVision analysis show significant opportunity for the U.S. geothermal energy industry, including as much as 60 gigawatt of electric generating capacity and 17,500 new geothermal district heating installations. Geothermal heat pumps could increase from 2 million to 28 million under the most cutting edge scenarios, advanced scenarios. So in increasing that geothermal deployment, we could strengthen our energy base, achieve a more stable power grid, and gain this economic and environmental benefit. Next slide. Geothermal heat pump opportunities are shown on this map, where under an aggressive breakthrough scenario, New England alone, so I've highlighted that in the red circle there, New England alone, it would provide under this scenario greater than 47,000 megawatt thermal for that region by 2050. Next slide. Opportunities for geothermal heat pumps as well. Oops, if you could go back one slide, I'm sorry. I think I jumped the gun on that one. sorry, yes, that was the district heating opportunities could, for New England alone, could provide 31,000 megawatts in the region by 2050, as shown in the dark area with the red circle. And now to the GHP potential. Thank you. Those opportunities under an aggressive breakthrough scenario in New England alone could provide 47,000 megawatt thermal for the region by 2050. Next slide. So over the last several years, the DOE Geothermal Technologies Office has sponsored about 7 deep direct use feasibility studies. So I'm not talking about a conventional direct use like you might find in the West where the heat is closer to the surface, rather deep direct use. And we looked at these areas that are in diverse geologic regions across the US. So in the Appalachian Basin, for example, feasibility studies were conducted in West Virginia, New York, and Pennsylvania. And you can see there some of the teams that worked in this area at West Virginia University, their Energy Institute. They also Cornell University and the National Energy Technology Laboratory worked with the folks at the West Virginia National Guard. And then in the Wasatch Range, and that's in Nevada, the town of Hawthorne, Nevada, and the U.S. Army Depot worked on feasibility study. And the Columbia River Basalt Group is another geological area. The Portland State University's feasibility study is also looking at deep direct use, and a little bit different than the others in that it's closer to what Mark was describing as aquifer thermal energy storage, but reservoir thermal energy storage. Working in partnership with Altarock and the City of Portland, Oregon Health and Science University. So they were looking at heating and cooling hospital complex. And the U.S. Geological Survey helped identify those resources on the Portland State team. Cotton Valley is another geologic area in East Texas where the National Renewable Energy Lab and Southern Methodist University worked on a feasibility study for Eastman Chemical. And the Illinois Basin, another geological area where the University of Illinois looked at the future agricultural corridor at the Champaign-Urbana campus. Facilities management plays a really important part on all of these teams. The facilities managers understand the energy use and the infrastructure. So that's a really critical part of these feasibility studies, figuring out what the energy end use is and how the infrastructure may exist or may need to be developed. Next slide, please. So low temperature geothermal resources used for district heating have the potential to address the needs of an evolving US electric grid by providing decentralized energy generation, where geothermal district systems function like microgrids, providing customers greater energy choices and the ability to participate by adopting geothermal storage, and also reducing peak load and providing that flexibility to the customer. So you see that described in the bottom left. But before I leave, I do need to say that even the centralized generation and geothermal is very important there for providing baseload power to balance the intermittent generation from sources like solar and wind. Next slide, please. So the Geothermal Advanced Energy Storage Initiative at the Department of Energy supports deep direct use, bidirectional energy storage, flexible generation research, And it supports one of the energy efficiency and renewable energy strategic initiatives called the Energy Storage Grand Challenge. And pictured here in the upper left is Energy Efficiency and Renewable Energy's Assistant Secretary, Daniel Simmons. Daniel is a strong supporter of the Advanced Energy Storage Initiative and of geothermal. Next slide. Our geothermal advanced energy storage initiative efforts to date really point to subsurface research as critical to achieving integrated thermal energy storage. Our national lab partners have initiated some new work in the various areas. One that Mark talked a lot about, borehole thermal energy storage at Oak Ridge. They're developing a heat pump integrated thermal energy storage. Reservoir thermal energy storage. We are looking at new cements for their insulating properties for underground storage, and also new shock resistant cements for baseload power that would withstand it would enable a power plant to withstand frequent thermal cycling. And finally, circling back to that subsurface research at Idaho National Engineering Lab, there's grid scale storage analysis underway that looks at the subsurface reservoir to offset the electric load when there is insufficient demand at the power plant side, and then provide that thermal energy back to the power plant when needed. And so that's why it's important to really understand the subsurface. Next slide. So lastly, this is my last slide. I want to mention those action areas that the Geothermal Technologies Office and stakeholders working on the GeoVision identified that are needed to address those GeoVision objectives. So again, the objectives being to increase access to the resource, reduce costs and improve economics, and improve education activities. So there were action items developed to address those areas. And, you know, the fourth or third area listed here is why I'm speaking with you today, in part to improve that collaboration and education and outreach. It's very important. And so this is where the homework comes in, because it would take another 20 minutes or so to go into detail, or longer, depending on your interest. So if you would go to the GeoVision, Harnessing the Heat Beneath Our Feet, and go to Chapter 5, which is the GeoVision Roadmap. And you'll see that a path forward. You'll find many detailed actions, such as something called Action Area 3, Maximizing the Full Range of Geoenergy. You'll see then sub-actions, just an example, a 3.2, a 3.4, things like investigating hybrid opportunities, addressing economic barriers to direct use applications and geothermal heat pumps. And you'll see lots of detail, sub-actions, deliverables, impacts. They're all stated for each of a number of key actions. So this would not be training without some homework. So I encourage you, please dive into the GeoVision Roadmap in Chapter 5. And just thank you for listening and learning. I very much appreciate it.
Thank you so much, Arlene. You've taken us through a journey. I know it's a very foundational work. We want to thank the Department of Energy. And it's really you leaving us with a roadmap and homework makes us take a look at all of the actions that need to come together to move the needle on geothermal. So we will read up Chapter 5. And thank you again for a very, enlightening study. We applaud the Department of Energy. So